Okay, so today is the last lecture on buckling. Next week we'll cover aeroelasticity. So today we'll cover buckling of stiffened panels. So we'll look at the interaction of columns and shells, which we covered independently last week, how they interact when we make a structure that's a combination of the two. So this is a typical wing cross-section, and I think I've stolen this picture from Flabel. We've got some stiffeners, also known as stringers, and skins on both front of the shot, front spar, rear spar, control surface. Now, the wing bending loads, any bending load in that wing is reacted as a tension compression couple. Because it's thin-walled, if it's normal positive end bending loads, the top surface is in compression and the bottom surface is in tension. And if we've designed it purely for strength, then the skins are very thin and very prone to buckling. So what we do is we reinforce them with stiffeners. We exchange some of the material that would have been in the skin for material that's got local second moment of area, and that local second moment of area stops at buckling. So we end up with the perfect compromise between a shell structure and a frame structure. Now we've talked about some of the initial instabilities that we might have to consider. So skin buckling, so we looked at shell buckling last week, so I've called it here skin local buckling. Stiffener local buckling we handled with an exercise at the end of the last lecture. So if you remember, we looked at buckling of the webs and flanges of an I-beam. That can also happen in our stiffener local buckling case. Inter-rivet buckling is a new one which we'll introduce today. Inter-rivet buckling is a form of shell buckling that happens between the fasteners. It's a fairly simple formula to work out whether we'll get buckling. And the other one that can happen initially before any of the others is panel global buckling. So if the whole panel buckles as a column, then the wing won't carry any more load and it's a catastrophic failure. So these buckling modes can be handled independently, but with a stiffened panel, the whole idea of a stiffened panel is if one of the buckling modes occurs, we don't generally want it to be catastrophic. The stiffened panel can carry more load beyond when the initial buckling loads occur. So what we have to account for too is final buckling modes, which are actually interrelated to the initial buckling loads, which are stiffener column buckling, as if after the skin has buckled, the stiffeners themselves become effectively independent columns. And we have to consider when they will buckle as columns. And then yielding or crippling of the stiffeners. So we'll go through each one of these cases independently, and we'll talk about how design guidelines drive the loads at which we need to set all of these different buckling modes. Now, skin local buckling, this is not new. We covered it last week. But if we look here, this slide is directly from last week. But what we need to know with a stiffened panel is how we determine all our dimensions. So it's not very useful just saying, well, the panel's 300 by 100. We need to know where you actually get 300 by 100. So in a typical wing like the one we've got here, the B is the distance between the stiffeners. So if you look at one little element of skin panel, okay, the B is the distance between the stiffeners, and the A is the distance between the ribs. So there's not a second rib shown here. But if there was another rib, A is the distance between the ribs. Because that defines a little unsupported piece of skin that we can use in our formula. And the thickness is defined by the thickness of the skin. So we can apply the simple shell buckling formula that we learnt last week, we can apply to a stiffened panel as long as we know how to define what the boundaries of the model are. And so it's fairly simple. We did an example last week, so I won't bother going through this example, but you can test yourself again if you want to. Buckling stress of a 300 by 100 by 2 plate subjected to a compressive loading. Okay, so if you see a question that says the stiffener spacing is 100 millimeters and the rib spacing is 300 millimeters, then you can sub it into this question here. Remembering that the compressive loads are generally applied in the direction of the stringers. So the B is always the distance between the stringers, and A is always the distance between the ribs. Okay, so stiffener local buckling we handled last week. That's if there's short spans, then stiffener local buckling can be an issue. It's not only for this case, but it becomes more prominent when the slenderness ratio gets shorter or gets smaller. So as beams become more stout, I suppose you'd say. And the analysis which we did last week treats each flange like a separate panel. So we just look at the buckling loads of each flange or web of the stiffener. And I won't go through an example because we did one last week. Now, inter-rivet buckling is when we are buckling the material between the fasteners. So if we went along a stringer like this one and we had a fastener every distance S, then there is a situation where if the S gets too big, that patch of skin will buckle in between them. And the formula is a little bit empirical. It is derived from similar theory to our skin panel buckling formula from last week, although there's a couple of different techniques. There's what's called the column method and the plate method, and as it turns out, when you reorganize these formulae, they're very similar. There's just a slight constant difference in them. But we look at the spacing between two fasteners from here to here. We call that distance S. We look at the thickness of the skin, and the only other parameter that we need is the fastener type. So if we have countersunk rivets, which we're showing here, these are countersunk fasteners here, we might have a C of 1 or 1.5 depending on the type of head that we're using. If we're using universal head rivets, we've got a constant of 3, or a hex head bolt or a high lock bolt, we might have a constant of 4. And you can tell from this table that these are what I would call empirical constants. They're derived from observation rather than theory. There's no theoretical reason why a bolt would have a constant of exactly 4 or a countersunk rivet would have a constant of exactly 1.5. It's something that people have done a few tests and worked out that that's the right kind of number to put in there. So let's just try subbing some numbers into these formulae to give it a go. And it doesn't matter whether you use the column method or the plate method. As I said, when you do the rearrangement, there's only really a very slight constant difference between the two. So we'll take that case up there. We'll assume we've got universal head fasteners. So we have a C equals 3. We've got AL 2024 T3 skin. So our E equals 70 gigapascals and our nu equals 0.3. Now, let's assume that our thickness equals 2 millimeters. Then what is the maximum stiffener pitch if we want our inter-rivet buckling stress to be less than 100 megapascals? Okay. I mean, if you're sitting next to someone, one person can use the column method, one person can use the plate method. So here I've written sigma IR, remembering that FIR is the same thing, it's just the imperial way of writing it, the American way of writing it. F is equivalent to stress. So for this kind of question, I often find it easiest to do the rearrangement of the formula before you sub the numbers in. So FIR squared equals pi to the fourth E squared over 2 root 3 S over square root CT. So I can take the bits at the bottom and put them at the top. So if I rearrange, I can put S up here and the stress down there. Okay, and S and FIR are inversely related to each other. So if you want the stress to be less than a certain value, it means that that defines the maximum value of S that you can have. Oh, sorry, this is meant to be greater than. What am I saying? It should be greater than 100 megapascals, but same thing, greater than or equal to. Generally, you want these to be higher than a certain value, not less than a certain value. What did you get? 83 millimeters. Okay. So, did anyone calculate the plate method version?
Yeah, for plate I got 87.
Okay, so S equals 87 for plate. Okay, the only difference as it turns out when you rearrange is that this bit is in one formula but it's not in the other formula. When you do the rearrangement of that, you end up pretty close to this formula. Okay, and I've done that completely incorrectly, haven't I? I've done that really incorrectly. I was meant to take a square root. I've squared it instead of taking the square root. So just ignore that equation. Absolutely ignore that equation. That's just gibberish. But the answer's right. Okay. So the three modes we've talked about so far, the stiffener local buckling, the skin local buckling, and the inter-rivet buckling are somewhat independent of each other. They depend on the same initial parameters, but they don't interrelate to each other necessarily. You can analyse them all independently. The kinds of buckling that we'll talk about next are ones that require, they're catastrophic modes. They're ones that happen at the end of the structure's ability to carry load, and we need to work out that they're history dependent. If the skin buckles, then a different kind of buckling mode will happen next. So we can't really look at them independently. So those local buckling modes don't necessarily lead to collapse. If the skin buckles, then the stiffeners can still carry load. If the skin between the fasteners buckles, then the stiffeners are still carrying load. So it's not going to cause our wing to just collapse in on itself. It can have performance effects. It can affect aerodynamic performance. It can affect a lot of other things, but it's not going to necessarily be catastrophic. Eventually, though, there will be a catastrophic mode. The panel itself as a whole will buckle, and once that happens, the structure can no longer carry any more load. And so the particular buckling modes that will lead to that collapse are stiffener column buckling and crippling, which we'll deal with independently now. So what happens in a stiffened structure as we start increasing the stress? So say this is the stress level applied to the structure, and I've got it's a repeating unit here. I'm only showing one section of it, but imagine this is a repeating unit of skin and stiffener. Once the stress gets to a particular level, the skin will start to buckle. And after the skin buckles, it doesn't carry any more load. Remember our skin buckling formula back here. This just tells us the stress at which it will buckle. It doesn't tell us what happens after it's buckled. The linear theory says it just keeps carrying that stress regardless of how much we buckle it. So it becomes ineffective at carrying any more load. So the stress in the skin panel stays about where it was. But the stiffeners haven't buckled. The stiffeners are still intact. So they start attracting more stress relative to the skin around them. So they behave like columns now, because the majority of the load is going through these independent stiffeners. We can analyse that unit as a column, but we can't analyse it exactly because we don't know how much load's being carried by the skin and how much is being carried by the stiffener. So we make an approximation, and the approximation is that the column that we will consider is the stiffener itself with a piece of skin attached to it that's a constant times the thickness of the skin. In this case, it's about 30, but we'll have a better approximation for it in a minute. But approximately 30 T of skin comes along with our stiffener, and we treat that like a column, and we work out its column buckling load. So let's do that right now. Okay, so most of these analyses assume that the panel is just a constant repeating unit of an unknown width, because we generally look at loads for a particular stiffener or stresses. We don't need to know the total load for the whole panel because we have ways of normalizing. If we know how much load a stiffener can carry, we can easily just multiply by the number of stiffeners in the structure. So the simplification that we use is that our panel is flat and that it's a constant repeating unit off to infinity. And we never try and calculate the total buckling load for the panel because we don't know how wide it is. We only ever calculate either the buckling load for the column or a stress. Okay, so let's give us some dimensions here. Okay, so the stiffener spacing we'll assume initially is 150. The thickness equals 2.5 millimeters. The thickness of the stiffener, which I'll give just a subscript S, but don't confuse it with thickness skin, I'll say is 2.8 millimeters. And I'll give some dimensions to this stiffener. So let's assume that's 30, that flange is 30, this flange is 50, and this flange is 30. And is that fully dimensioned, everything? Yeah, it has. Okay. So one of the simplifications that we make, and it's a fairly reasonable one, is that these will only ever buckle about an axis parallel to the board. So the buckling modes are just going up and down the board. We don't have to worry about buckling around other axes because the skin is still intact. Even though it's not carrying any extra load, it's still going to support any motion of the stiffeners laterally across the board. What it won't support is motion of the stiffeners up and down. So any bending as a result of the buckling will happen about an axis that's parallel with the skin. So that's the first simplification to make our life a bit easier. Okay, so let's work out what the unit of stiffener that we're looking at is. I'll draw it a bit bigger. Here's my stiffener. Here's my piece of skin. My fastener line. Now, how much skin do I need across here? Yeah, so what's that? 75 millimeters. So in this case, I've actually, because of the skin buckling, I'm assuming that only half the skin is really active in helping this column resist buckling. $30, $50, $30, 2.5, 2.8. Okay, so this is now just a complicated cross-section. We can work out the IXX of this, or we can first work out the centroid. We can work out the IXX, and we can work out its buckling load. So we generally work out the centroid from the skin midplane as a datum. So A skin, I'm just going to use the subscript SK now, just because we're going to have two areas that we need to deal with. Area skin equals 75 times 2.5. Area stiffener equals 2.8 times 30 plus 50 plus 30. Y skin equals 0. And we'll use this as our positive Y downwards. Y stiffener equals what? Where's the centroid of the stiffener? Yeah. So it's 25 to the center of the stiffener, plus if you wanted to, you could add some thicknesses in here. You could add the skin thickness potentially, but I'm assuming it's not the best assumption, but I'm just going to assume the thickness effects are small. So I'll just take out the thickness of the skin and any other thing. So I'm assuming that the midplane of this flange and the midplane of the skin are coincident, and I'm only looking at half the flange width, or half the web depth, sorry. Okay, so y bar equals sum of AY over sum of A, which is A skin, Y skin, plus A stiffener, Y stiffener, all over A skin plus A stiffener. So did someone calculate these two up here so I can put them in?
187.5. 308.
That sounds about right. Anyone else want to make an adjustment to that? 15.5, and what are the units? Millimeters. Okay, it's a distance. So it's saying that 15.5 millimeters from the skin, so somewhere about here, is the centroid of the whole unit. So any buckling is going to be about a neutral axis that runs through there. Okay, so what's the next thing? If we're going to calculate the IXX for the whole system, we're going to have to use the parallel axis theorem a few times. We're going to have to work out the IXX for each part independently and then use the parallel axis theorem to move them around. So the first thing we'll do is work out IXX of the skin about its CG and IXX of the stiffener about its CG or its centroid. Now what's IXX for the skin around its centroid? It's a nice easy one that doesn't require any calculation. 0. Okay, the thin-walled approximation, the skin is thin, it's got no IXX about its centroid. IXX of the stiffener about its CG, that's a little bit trickier. It's going to be, because we've got a nice symmetric case here, it's going to be IXX of the, we'll number these actually, just so I've got a nice numbering system. Okay, so I'm going to call them element 1, 2, and 3. Is going to be IXX1 about the CG plus IXX2 about the CG plus IXX3 about the CG. So for 1, that's just going to be AD squared, okay, where D is the distance to the centroid. So I'll just substitute the numbers in now. 30 times 2.8 times 25 squared, because the centroid of this is right in the middle here. The IXX of element 2 about the CG is going to be a BD cubed on 12 IXX, because the centroid is actually at of that element is at the CG already, so we're just accounting for the depth of it. So that's 2.8 times 50 cubed over 12. And this one again is 30 times 2.8 times 25 squared. So someone got a value for 134166. So if we just said 1.34 by 10 to the 5 millimeters to the 4th. Okay, so IXX total equals IXX of the skin about its CG plus A skin times the distance to the CG squared, or the centroid, plus IXX stiffener about about its own CG. Actually, I've got a confusing set of subscripts here. I'm just going to leave that as d squared. Don't put a subscript on that because it's just I'm confusing CGs, so we'll just leave the subscript off. Plus a stiffener d squared. We're aware that these d's are the distance to the column centroid. Okay, they're not they're the distance from the centroid of the skin to the centroid of the column, from the centroid of the stiffener to the centroid of the column. So let's sub in some values. Equals 0, the first term, plus A skin is up here, 187.5 times what's the distance from the skin centroid to the column centroid? Yeah, 15.5. It's just y bar. Okay. So 15.5 squared plus 1.34 by 10 to the 5 plus A stiffener is up here, 308 times, now this one's a little bit trickier, the distance from the column centroid to the stiffener centroid. So we've got 25 minus 15.5 all squared. So we need to know the CG of the whole system is here. The CG of the stiffener is here, and we need to know the distance between the two. Okay, so let's work out the total IXX here.
We got
2.07 by 10 to the 5. Agreement? Yep, everyone? Excellent. So now we're in a position to work out the buckling load for this little column. So I'll leave that visible just there, and we'll work out the buckling load for the column. So P critical, so the critical load at which the column will buckle, equals K pi squared E I, and in this case I'll put the subscript XX on, over length squared. Okay? Actually, I've made a mistake there. You should never have K and length effective in the same formula. It should either be K and length squared or length effective squared, because LE incorporates the value of K already. So just either scrub out your K or scrub out the subscript E in your notes. So let's have a look at this and see what we need. Well, firstly, we need to know what the column's made from, but our standard assumption is that we're using aluminium. So 70 gigapascals. Our IXX we just calculated. And so the bit here that's important is the length. Now, what defines the length in a structure of this stiffener? Yeah, the distance between the ribs. So we call this, it's the rib pitch. So when I use pitch, I mean the spacing between a repeating unit. So the pitch of the ribs determines this length. And we don't bother with a K higher than 1. The simply supported case is a reasonable assumption. Generally, our ribs are fairly poor at resisting rotation, so that the stiffener is just simply supported at its ends. It's not clamped or anything. So we generally just put L equals, or LA equals L in there. So the spacing between the ribs. So in this case, let's assume that L equals 1 meter. That might be a little bit high, but we can work out the critical buckling load. Okay, remember, this is 1,000 squared. Throw out an answer if you've got one. 143 kilonewtons. That seems a little high, but it could be all right. Is anyone else?
So I was just assuming that the 1 meter is like the effective. I think I missed that. I was assuming that 1 meter.
Yeah, the effective length. Yeah, so we just assume that if we're looking side on, our skin's going to look like this. We're going to have ribs every certain distance that will be, and the stiffeners will run through the ribs, so it's very hard for me to draw that on the board, but the stiffeners will run along the length of the wing. And so because the ribs are fairly thin, just like the skin and the stiffeners, they provide very good constraint up and down, but they don't provide very good rotational constraint. So when this buckles, they'll buckle in a mode that's like that. So if you see a half sine wave, then it's effectively K equals 1 or LE equals L. So has anyone got a change on 143 kilonewtons, or are they? So we'll end up with this divided by this will be about 0.2 times 70,000 times 10. So 10 times 0.2 times 70,000. What have we got here? That crosses out to 2. It's 140,000, so yeah, we're about right. So it's always handy if you've got a very quick approximation technique to work out whether you're all right. Okay. So you'll notice that this gives us a load. It doesn't give us a stress. So we need a way of comparing this to a stress, which we'll talk about later. But just be aware that the different calculations that we're doing are actually giving you different results. You can't compare this directly to the skin buckling load that we found earlier because they're a different set of units. It's like comparing apples and oranges. So we need a way of normalizing all of our results to one measure so that we can compare them. And we'll have a look how to do that in a little while. We just covered a stiffened column buckling case, and we made an assumption in there that the width of the skin that was being effective in our column was 30T. Now, if anyone's been looking at the notes and skipped ahead a couple of slides, they'll notice that that's just a guess, and there's a better way of predicting what that effective width should be. So that 30 seems fairly arbitrary, but it turns out that the 30 is derived from a more complicated formula. Now, the way that stiffeners and stiffening elements are attached to structure varies dramatically through a given wing cross-section. So if we look here again, I think this is a picture from Flabel, we can see that we have stiffeners attached here with 2 fasteners. We have stiffeners attached here with 1 fastener. We have spar caps that have multiple fasteners attaching them, and a different situation here with a rear spar cap. And so we need a way of working out, if we're going to do these column calculations, and column buckling and also crippling, which is a case that we'll consider in a minute, both are column type calculations. We need to have a more rigorous way of working out how much area comes along in our calculation. And we do a calculation for what we call effective width, so the effective amount of skin that comes along. So in these different cases, the effective part of the skin is coloured in black. So it's not necessarily to scale, but you can see that the effective bit of skin for each attachment is coloured here, and I'm just now going over it in red. Different amounts will come along depending on the thickness and on the attachment method. And we'll have a look at how to calculate how much comes along for the calculation. So really we're just solving for this distance up here. What should that be? So this is the analysis that Flabel provides, and again, this is an empirical analysis. If you see constants in an equation like 1.7 and 0.62, you should immediately think to yourself that this is not something that's been derived from first principles, because it's very rare that you'll get a constant like 0.62 appearing in first principles analyses. So this is something that people have done tests on and derived formulae that worked. The effective width in general, if we've got a bit of skin that's attached at both ends, so here if this skin continues in both directions, then WE is given by this equation here. So 1.7 times the thickness over the compressive modulus, and this is a new thing that we haven't seen yet. This FCC is the crippling stress. And I know it seems a bit odd to use a value before we know what it is, but I promise you we'll calculate it in a minute. It's just easier to start this way than the other way around. So if it's related to a stiffness, but it's also related to some kind of failure stress. So we're starting to see that our buckling isn't as pure as it used to be. If some of our calculations are dependent on material yielding, we're not dealing purely with elasticity anymore. This is now starting to bring in material failure. So this is the first hint that our elastic assumptions are starting to break down. Now, if the skin doesn't continue, so as in the case I've shown here on the right, this bit of skin continues off, but this is a fixed end. If it doesn't continue, then we use a slightly different value. We use this WF. Okay. It's just got a different constant in front. And the only other change that we make is if the inter-rivet buckling stress is less than the crippling stress, then we also normalize with another ratio. The reason that is if you imagine that the skin between the rivets is buckling, so that's actually the skin that's meant to be being effective. If it's buckling, it's carrying less load. So if the inter-rivet buckling stress is less than the crippling stress, then it's starting to not pull its weight and it's not doing its job. The one other constraint which I haven't shown on this slide is that we don't double count area. And what I mean by double counting if we had something like a J toggle, WE for this fastener might be that range. WE for this fastener might be that range. We don't double count the effective material in between. We just use the overall effective width in our calculation. So we normally sum up all the pieces of effective width. In this case, we just use the overall. So let's do an example which we will use again in a minute. So hopefully you can read the dimensions here. If you can't, I can read them out. But we have a Z stringer on a bit of fuselage skin, and the skin thickness up there is 0.05 inches. The compressive modulus of the skin is 10.7 MSI. The Poisson's ratio is 0.33. The crippling stress is 30.5 KSI. And the tensile ultimate is 59 KSI. We may not need the tensile ultimate at this stage. But what we have to do is work out the effective area in compression and the total load that the stiffener can carry. And then we can work out the maximum load in tension as well. But we're skipping a few steps ahead if we do this full problem. Let's just do the effective width calculation first. What units are we going to get out here? Inches, the same units as our thickness. Because this is a stress, this is a stress, they'll cancel each other out. So we get the same units as our thickness. So 1.7 times 0.05 times the square root of, remembering that 1 is in KSI and 1 is in PSI, so we need 10.7 by 10 to the 6 over 30.6 by 10 to the 3.
$1.6.
1.6. Any advance on 1.6? Okay, so how many T is that? 32 T. So we approximated 30 before. We've got 32 here. Depending on the ratio in here, it's going to always come out somewhere around 30. The big place where it's not going to be 30 is if you didn't have a continuing bit of skin. If you had a bit of skin that stopped here, the constant is much lower, so the amount of skin that you get is much lower. All right. So we can't answer all of these questions yet, but this is a typical kind of problem with a stiffener, and it's directly applicable to your assignment and potentially directly applicable to exam questions as well. You've got stiffened structure, you've got your skin, you've got a stiffener attached to it. You know your compressive loads because you've calculated your compressive loads in the structure from your bending stresses. Once you've got your compressive loads, you need the allowables to compare it to. And the allowables are the inter-rivet buckling stress, the compressive failure load for the stiffener, tensile failure load for the stiffener, and any margin of safety that may be there. So let's work out some of these. What's the inter-rivet buckling load for this particular problem? Okay, and I should have Flabel with me and I don't. Okay, the S equals 0.73 inches. And I'm not sure what fastener head types these are. I think they're just called rivets, but I'll jump back to that slide. No, they're countersunk tension head rivets. So they're C equals 1.5. In Flabel, he describes this a little bit in a little bit more detail. So what does the inter-rivet buckling stress equal? Just one of them. Whichever's easiest to calculate. There's no guidance as to which one's a better method. They're both approximate. So has anyone got a value for the inter-rivet buckling stress?
Seems large, but I have 69.5 kilopounds. Whatever that is.
It should be
175 KSI.
it should be a number fairly close to this.
F is in a stress, not F.
It's a stress, yes. Stress. It should be very close to that.
Oh,
I mean, a bit above or a bit below. Actually, it'll be below. So let's chuck the formula back up. Stay there. Pi squared times, we'll do it all in KSI. So pi squared E is 10.7 by 10 to the 3. All over 2 root 3 times square root 1.5 all squared times S squared, which is 0.73 over 0.05 squared. Or alternatively, you can use this form. This form's probably a little bit easier to use in practice just because you don't have fractions on fractions on fractions. So let's use the, sorry, that shouldn't have an inch. That should just be 1.5. FIR the other way is 1.5 times pi squared times 10.7 by 10 to the 3 all over 12, 1 minus 0.33 squared times 0.05 on 0.73 all squared. Is it big, is it?
It's giant, yeah.
Okay.
60-something.
All right, in this case, it could just be the stiffener pitch, the fastener pitch could be small enough that it's not an issue. So what value?
For that one, 61, and for that one, 69, for the other one, 61.
61 KSI. Okay. It must be another example where they're about the same. But in this case, what that means is because the inter-rivet buckling stress is higher than the crippling stress, we don't have to change our effective width. If this came out lower than the crippling stress, then we need to change our effective width. So in terms of answering the question, what this question is saying is we've done a computer analysis and it says that the maximum tension load that could be in this stringer is 17 kilopounds, and the maximum compressive load in this stringer is 8.5 kilopounds. Then we have to determine what the allowables are, what the column can withstand, and then we can work out margins of safety. So we've worked out the allowable inter-rivet buckling. This is actually, I should have written stress. Okay, if we wanted load, then we have to multiply by some area somewhere. But that's generally a crippling load. So if we wanted to work out the maximum compressive failure load, we need a crippling analysis. So I won't go to that yet. But for this simple example, because we already know FCC, it's given, P crippling is just FCC times area total, where the total area is area stiffener plus the sum of the effective widths times the thickness. So this is an area, this is an area. So in our problem, it's the area of the stiffener up here plus the area of the skin that came along with it. But as I said, we won't do this calculation just yet because we haven't worked out how to calculate this FCC. The stringer tensile failure load. In tension, we never need to worry about effective widths because in tension, things don't buckle. So in tension, all the skin is active. So if we wanted to work out the tensile ultimate, we have the force that the stiffener can carry in ultimate tension is the ultimate tensile stress of the material times the total area. In this case, the total area is the total skin width between stiffeners. So 9 inches. So let's work out what that A total is. AT equals A stiffener plus 9 times 0.05. A stiffener equals, we'll have to look at our geometry up there, and I'm just going to do some approximations. 0.58 times 0.05 plus 1.5 times 0.08 plus 1.1 times 0.63. Okay, and I've double counted a little bit of area in there, but that doesn't matter too much. So all I'm doing is just adding up the total areas as I go around my stiffener. Now this has to be an extruded stiffener. You can't make a rolled stiffener that's got different thicknesses as you go around it. This has to be an extruded stiffener. And because it's got sharp corners, you can tell it's an extruded stiffener. So what did anyone calculate this? 0.224 inches squared. And what did you get for a total? 0.063, sorry, yeah, there's a 0.063 in there.
Gives you
0.2183. Anyone else going to, I think that's, from memory, that's pretty close to what's in the book in Meg's, in Flabel. Anyone else going to change their answer for this? No. The total area then, that's 9 times 0.05 is 0.45, so we should end up with 0.66 or 0.67 or something like that. So what is it? 0.67 is probably close enough. Inches squared. So the PTU equals FTU, which is 59 KSI, times 0.67 equals anyone got a value? What the units of this going to be? Pounds per square inch. Square inches, we'll get pounds. Anyone got a number? 40,000? That's probably pretty close. Okay, 40,000 pounds. So generally, we'll find that in tension we have large margins of safety because these structures are much more prone to compressive failure than tensile failure. So margin of safety equals allowables. So PTU over applied, P tension minus 1. So the allowable is 40,000. The applied, which is on the next slide, is 17,000. Oh, 230. Minus 1. So the margin of safety will be quite high. So it'll be 1.2 or something like that. 1.3. Okay, remembering that a margin of safety of 0 means it's passed. So it's got more than twice the capacity it needs. The reason is because it's thin-walled. Thin-walled structures are very good in tension, but they're not very good in compression. So the tension case is never going to be the critical case. Okay. Let's move on to crippling, which is this thing that I've been talking about for a while. So we can think of compressive failures in three different ways, or put them into three categories. There's global instabilities, and instabilities are buckling. So I've used this bit of plastic to demonstrate that this is an instability. It can't carry any more load, but it's not failing. I haven't damaged the material in any way. It's just elastic. So we can have geometry-dependent instability and stiffness. There's no material strength that would go into that calculation. We can have block compression failures. If I took this eraser or duster and I loaded it until it failed, it's not going to buckle, it's just going to yield and crush. So if the member is stout and thick, then we'll get material compressive yielding. In between, there's an intermediate mode, which is applicable to stiffened thin-walled structures, and that's called crippling. So it's a mixture of local instability of stiffeners and material yielding. So what happens is stiffeners themselves are like their own little stiffened structure. The stiffener has webs and flanges, and when the webs and flanges start to buckle, the corners of the stiffener act like little stiffening elements. So the corners of the stiffener end up with higher stresses than the webs and flanges. And because the corners end up with higher stresses, they're the first things to fail. So what eventually happens is if we keep loading our columns until we hit, if they're not going to fail through column instability, so column buckling, then eventually some material is going to give way. And in thin-walled structures, the material that gives way is material in the corner. So you end up somewhere along the corners of your stiffener, you'll get yielding failure. But the average stress on the stiffening element at which that happens is less than the compressive yield stress of the material. So to use it in calculations, we need to work out what that stress is going to be. And again, we have another empirical calculation from Flabel, and it looks fairly complicated, but I'll go through it step by step. It's based on breaking down a stiffener into corners for our calculation. So every stiffener can be broken down into corners. Well, these all have skin attached to them, but crippling calculation just starts with a stiffener calculation. We don't worry about the skin to begin with. Now, the breaking down of corners we do at the start of our analysis. So what we do is we split anywhere where there's a connection between two corners, we split it halfway, and we say that's corner 1, that's corner 2. In this case, we have 4 corners, 1, 2, 3, 4. 1, 2, 3, 4. For an L stiffener, we just have 1. And for any case where we have a junction where there's a T-junction, we treat one half of the T-junction as 1 and the other half of the T-junction as 2. So something like a J has 3 corners. 1 here, one that way and one that way, but they split in the middle. So once we know how to break the stiffener down into corners, then for every corner we calculate the crippling stress. So every corner has two thicknesses and two lengths. And using those thicknesses and lengths here, we substitute into the crippling stress formula to work out what the crippling stress is. The provisos are that if the crippling stress is higher than the compressive yield stress of the material, we just use the compressive yield stress of the material. And this constant in here, we have to work out. There's a pesky constant here, and that constant is dependent on the arrangement of the reinforcement of the corners. So we have to count the number of free edges that a corner has. And by free edges, I mean edges that are supported or unsupported by the rest of the stiffener. So if we look at this L stiffener, there's no extra material out here. So this has what we call two free edges. This corner here, corner 4, this edge is free, but this edge was connected to another part of the stiffener, so it's not free. So this one has one free edge. Corner 3 has 0 free edges. Here, both 1 and 2 both have 2 free edges because both ends of the corner are unsupported. So it's really, you just work out how many free edges each corner has, you select the appropriate constant, and then you feed it into the calculation. Once you've worked out the crippling stress for every corner, then you do a weighted average by the area of each corner. So we'll do an example. And if you notice, this is the stiffener that we had in our previous calculation. And again, this example is from Flabel, so if you've got a copy, you can follow along. And because with these stiffeners, sometimes our thin-walled approximation is not particularly good because the dimensions here start getting comparable, you have to be a little bit careful about how you measure your dimensions. So technically, the theory wants you to calculate your dimensions from the midplane of the other arm of the stiffener. So in this case, we should work out what our midplane dimensions are. Okay, so how many corners do we have here? 2. Corner 1, corner 2. And I'm going to put a very narrow slice directly between the two. So the first thing, free edges. How many free edges have these corners got? One each. So the C that they're going to use is, assuming it's made out of aluminium, is 0.317. Now, we can have B1, B2, T1, and T2. So for corner 1, let's assume this is B1 here. That is 0.58 minus 0.04. So we get 0.576. So what I've done is I've taken that dimension and subtracted half of this dimension. 0.54, sorry, what am I doing? 0.54, I've just taken off the wrong number of decimal places. Not enough sleep last night. 0.54. B2 is 1.5 divided by 2 to get us to our halfway point, minus half of the top thickness, so 0.025. So I've got 0.75 minus 0.025 is 0.725. Have I done that one right? I hope so. Sorry, that's in the wrong place. It's there. So I did do it wrong. You can tell I went to bed at 2 o'clock last night. The fun of having a new baby. The T1 is 0.05. T2 is 0.08. Okay, so I'll leave you guys to work out what to put in here. Now we're going to need some more columns. So I'll just put a squiggly line across here. 1 and 2. The extra columns we need are area, B dash on T, and FCC and FCCA. So for argument's sake, I'm just going to simplify the area calculation. Area for 1 will be 0.54 times 0.05 plus 0.75 times 0.08. So it's just B1 T1 plus B2 T2. We might not quite get the area right in the corner, but it'll be pretty close. B dash on T, as it says up there, is B1 plus B2 over T1 plus T2. So can someone calculate these two for me? I mean, if they're independent, so one half of the room can calculate one and the other half can calculate the other. Or if you're sitting next to a friend. So has anyone got an area for one? 0.085. Yeah, it's probably in the right ballpark. And that's in inches squared. So if I was doing this table in an assignment or in something that I needed to be pedantic, I would write inches squared in here. I'd write inches up in these ones. B dash on T, what did... 10? Sounds about right. Has anyone else got a... 9.7. We'll leave it as 10. Doesn't make too much of a difference. Okay, so FCC, the last calculation here is to work out what the crippling stress is. Now, the crippling stress, what units is it going to be? I'll clear all my ink off because it's just getting in the way. What units is our crippling stress going to come out in? PSI, but we've got to be careful though because we're multiplying two stresses together and then square rooting. So those two stresses that we multiply together have to be in the same units and then the crippling stress will be in those units. So if we use KSI, we have to use it for both. If we use MSI, we have to use it for both. If we use PSI, we have to use it for both. Because often you'll see E quoted in MSI and F quoted in KSI, or they'll be in two different units. So we have to be very careful about how we use them. And B dash and T is dimensionless, B dash on T. So we're now in a position to work out this term. And then we can work out this term.
What's FCY?
The compressive yield stress for the material. So that is 34,000 psi. So if everyone's got that, I'll just jump back so that people can see the formula. Now remember, if your FCC value comes out bigger than 34,000, you just use 34,000. So what did it come out as? 35. Okay, so in this case it's 34,000. But for the other one, for the other arm of the stiffener, it will be less than. And now we go FCC times area, because the crippling stress for the whole stiffener is the weighted average based on areas. So we multiply every crippling stress times the area of that corner, and divide by the sum of areas, and we get the total crippling stress, or the average crippling stress for the structure. So on these two columns, we need a sum and a sum. And then FCC equals sum FCCA over sum A. Sorry, that's one we don't need a sum. We need a sum there. Okay. So the crippling stress should come out to look something like this value here, because that's the same stiffener. Okay? If that's the same, if we've got the same stiffener, we've got the same compressive stress or crippling stress. Okay, so I'll leave you to do the other half of the calculation yourself, and the validation check that you've got to make sure it's right is that you get a number that's close to that one. So how do we use the crippling stress? Well, I discussed that earlier. To get to the compressive load, it's the compressive stress times the area total, where the total area is the stiffener area plus the effective area of the skin that comes along for the ride, so WET. Now, before we have another break, I'll just show you a picture of a real buckling result. And we'll compare this to our design calculations in a minute. This is a test where someone has plotted the shortening, so the compressive displacement of the panel. So if it starts at this length, how much shorter it gets as you're loading it up, versus the load that it's reacting back against the machine that's compressing it. And these are all on different scales, so if they all look like they're well buckled, it's because we're blowing up the scale by a factor of 10 here. But initially everything's linear, and then there's a little kink, and that little kink is one of the skin panels starting to buckle. And as we go up further, the gradient's gradually dropping off, and it's more buckling is spreading. And at some point, the gradient changes to be nearly flat, and that's when we're starting to get stiffeners coming out of plane. So this is when the global buckling is starting to happen. And what I mean by that being catastrophic is really if you load the panel to any load above, say, here, the structure completely collapses. There's no more load that it can carry above that collapse load. So the distance between that first stringer buckling and the total collapse of the panel is basically nothing. So as soon as the stringers start to become unstable, the whole panel just collapses into a heap. So what we have to do is pick our design limits so that these events happen appropriately relative to the loads on the airframe so that we don't end up with wings that do this. Okay, so everything we've done to this point is looking at analysis of these structures. So the last step with stiffened panels is to go from analysis to design. So if we're already given the geometry and the structure, analysis is a fairly straightforward process. Although the calculations can be tedious, at least it's all in one direction. We know some geometry, We work out some critical stresses and we compare them to our applied loads. It's a much more complicated process to design a stiffened panel because we don't have any of that information in the first place. So the first thing we need to do is a way to compare our buckling analysis results, because part of the design process is analysis. It's one block in the design process. Now, we get different results. We get stresses from some of our analyses. So if we do a skin panel calculation, we get a stress. If we do a stiffener column buckling calculation, we get a load. If we do a crippling calculation, we get a load. But having a high stiffener buckling load is not helpful if your stiffeners are a metre apart. We need a way of comparing stresses that we get from some of our calculations, like local buckling stresses, to loads that we get from global calculations. And we need a common measure, and the common measure we normally use is the average critical compressive load per unit width of the panel. And so loads are in newtons, for instance, or in pounds. Stresses are in newtons per millimetre squared, or megapascals, or in PSI. What we use is the intermediate between the two. We use loads per width on the panel, which means that if we have our repeating panel, a load per width accounts for how many stiffeners we've got, and it also accounts for the fact that we've got a repeating unit. So the load per width on this unit is exactly the same as the load per width on this unit, because if you just multiply the same thing by n, you get the same result. The load multiplies by n, but the width multiplies by n as well. So we always normalize back to this n, which is load per width. And we've seen that n pop up in other calculations before. We've seen the n pop up in composites calculations and some of our other solid mechanics calculations. We've seen this n. Now, if we've got a stress calculation, to get to n we need to multiply by a distance. If we've got a load calculation, we need to divide by a distance. So we need to work out what those distances are. So let's just take one of our units here. So this is one repeating unit. And assuming we've been given a critical buckling stress, and I'm just going to use critical just for any generic buckling stress that we've been given. And that unit has a width b. How do we get to a load per unit width? Well, the first thing is we need to get to a load. So to get to a force, we'll times our critical stress by the total area. And then to get to a force per unit width, we divide through by that width b. So I'll write that up a bit bigger. So N critical equals sigma critical times AT over B. Now, we're going to have a bit of a closer look at this. this is an area divided by a distance. So it's got units of effectively a thickness. And what we call this is T star. A total over B. Okay, and it's called the effective thickness of the panel. Now the total area we can split up into a couple of extra pieces. We can say that's the area of the stiffener plus the area of the skin where T is the thickness of the skin. And so we end up with this simplified version of it. This T star, it's often referred to, or effective thickness, is equal to the area of the stiffener over the pitch of the stiffener plus the thickness. What it's equivalent to is taking the area of the stiffener and smearing it out over the width so that you've got a total thickness there of T star. So it's equivalent to just spreading the area of the stiffener out over the total width of the repeating unit. So the formula that we normally see quoted in things like Megson is that the critical load per unit width is equal to the critical stress times T star. Now let's consider the case where we were given a load initially. So assuming we've done an effective width calculation and we've done our stiffened column buckling calculation, we get a critical load out. So it's very easy to go from our critical load to an N. So the N that we use for comparison is the critical load over the spacing. So now we've got a way to compare critical buckling stresses to critical buckling loads, and it's independent of the width of our panel. We can have as many repeating units as we want, and we're comparing apples to apples. We're not trying to compare different sets of units. So if we want to say what buckling will happen first, will the stiffener column buckling happen first, or will the stiffener local buckling happen first, we just compare the values of N. We don't have to worry about comparing loads and stresses and everything. We just compare the critical loads per unit width. So that's very helpful for us in a design process. Okay. The next step in the problem is that we need to understand allowables versus applied loads. So what we've calculated here are allowables. They're the amount that we can apply of load we can apply to the structure before failure occurs, or before instability occurs. That doesn't mean that's how much is applied in general. In general, the applied load could be anything. It could be zero, it could be negative, it could be positive. It can have any range depending on the flight loads. So to tell whether our structure's failed, we have to compare allowables to applied loads. But the question is, what applied loads? We know that when we design aircraft, we design them based on limit loads, we design them based on ultimate loads, we design them based on all sorts of different load cases with control surfaces deployed, doing certain maneuvers, different load factors. The way we decide what we're comparing to is based generally on this idea that we have non-catastrophic and catastrophic buckling modes. So what we assume is that there is the behavior of the panel up there is shown in blue. So if we weren't considering design at all, the behavior of the panel is shown in blue. So initially, we'll get some kind of linear behavior. You'll get a first non-catastrophic buckle, like a skin panel buckling. And then beyond that, you'll get some catastrophic buckling, like a stiffen or column buckling, a collapse. The loads we compare to, the applied loads, limit and ultimate, we assume that no non-catastrophic buckling happens below limit load and no catastrophic buckling happens below ultimate load. Because if we take a step back and think about what limit and ultimate load actually are, ultimate load is the load at which the aircraft will break, or it has to survive ultimate load for 3 seconds. If it doesn't, if you go beyond 3 seconds, well, the aircraft's not designed for that, and the aircraft could break if you sustain ultimate load. So if we just touch ultimate load, we don't want any catastrophic events to be happening. We want the structure to still be maintained. That's why we position ultimate load next to the collapse. But it doesn't really matter if the skin buckles below ultimate load, because if it's not catastrophic, it's just unsightly. It might degrade our aerodynamic performance, it might cause some fuel to leak or various other things, but it doesn't break the panel. So it's all right as long as it doesn't happen below limit load. So most of the time the aircraft's in this regime. If something really, really, really bad happens, it might get here. But we design the ultimate load. The aircraft should never see ultimate load. So to break the wing, you'd have to get all the way up to ultimate load. So this is how we base our design load. So when we've calculated all our allowables, the loads we compare to come from limit and ultimate. And the ratio between limit and ultimate is 1.5, or between ultimate and limit. So if you know your limit load, you can find your ultimate load by multiplying by 1.5. Now this doesn't necessarily help us from designing the geometry of the panel load. The geometry of the panel is very complicated. We have inputs on one side, which might be things like skin thickness, fastener spacing, stiffener geometry, panel length, fastener type, stiffener spacing, all these things which we have to choose to design our panel. And on the right-hand side, we have all our outputs: stiffener buckling, skin buckling, the weight of the panel, how hard it is to manufacture, crippling, and the list could go on. And the relationship between them is really kind of messy. All of them interact, and there's no nice, clear way. If you knew what these loads had to be, which you can find from your design, you sort of know what the things on the right-hand side should be. It's not a process that you can reverse. You can go from this to this, but there's no way in using the mathematics to reverse that process. So this is where design comes in. We don't have a perfect optimal solution. You have to try something, see how it affects the output, and then make decisions about what to do to the input. And so we end up with what we call a design loop. So we start with a trial, we start with a guess, we do an analysis, we evaluate the results of our analysis. If we need to, we refine the design, reanalyze, and repeat this loop until at some stage our evaluation says, yes, that's an effective design, and spits out an answer. Now, this bit is what most of this course has been involved with so far, but next semester and in fourth year, you'll really try and go down this path. And in this semester, I will give you a taste of this process too. I'm going to make an adaptive tutorial which has a design element to it, which I'll show you the seed of today. It's not quite finished yet. But these are actually quite tricky things to do. Everyone thinks the analysis is the hard bit, and I can promise you the analysis is the easy bit. The evaluation and the refinement of your design is where the real mental challenge comes in. So if you do an analysis and your applied loads end up less than your allowables, great. Excellent, you've got a working design. But I could guarantee you that I could make my applied loads less than my allowables by machining my aircraft out of a big block of aluminium that didn't have any holes in it. Now, does that make it a good design? Well, no. It makes it a working design, but how do we evaluate whether it's a good design? Well, you have to calculate the costs associated with your design. And by costs, I don't mean dollars. I mean things that will cost us money, both in terms of weight in the aircraft, how hard it is to manufacture, how many different manufacturing processes we've got. So the kind of costs we might consider are the weight of the panel that we design, and the best way of evaluating the weight or comparing the weight of one design to another is with this T star value, because it's independent of the width and the length of the panel. So if we get one panel that's got a T star of, say, 6 millimeters and another that's got a T star of 4 millimeters, then we choose this one because it's lighter, or we attempted to choose that one because it's lighter if it meets all the other design constraints. The number and type of stiffeners, so if you can choose different types of stiffeners, but they all have their own manufacturing constraints and manufacturing complexities. The more stiffeners you put in, the higher your buckling load will be, but also the heavier it's going to get. Because if you've got 10 stiffeners across the width of your panel versus 4 stiffeners across the width of the panel, you've got more weight, more structure. So all of these things cost us as when we make our design. Now, we compare one design to the next design and weigh up those costs and determine which one we're going to accept. And there's no hard and fast way of doing that weighting. It relies on previous knowledge, design guidelines, and knowledge of how these structures are going to be made. But if one design is better in all of these aspects, then it's clearly a better design than if design A ticks all of these boxes better than design B does, then you choose design A. That's a no-brainer. But when there's disparity, we're not sure which way to go. If you need to refine, you do a refinement, and that refinement is along these lines. If you decrease your skin thickness, you decrease your weight, but you also lower your skin buckling load and potentially your panel buckling loads or your column buckling loads. If you decrease your stiffener pitch, you make your fasteners closer together, you increase your weight, but you increase your skin buckling load. So it's a matter of tailoring the variables until you get the right answer. And I will show you an example of a little simulation that I've built that I'm going to embed in an adaptive tutorial for you. But it's not quite ready yet. Okay, so here we have a set of input parameters for our panel. So we have skin thickness, stiffener type, stiffener pitch, stiffener thickness, stiffener depth, flange widths, fastener type, fastener pitch, and panel length. So they're the input parameters that you need. Here's a little drawing of the stiffener, what it looks like, so you can tell whether it's a sensible proportion, whether stiffeners are going to run into each other. Here is the buckling loads, and I'll turn off, I've got an option to save a current model state, so I'll turn off the saved model state. Okay, so for this particular design, the limit load is 600 newtons per millimetre and the ultimate load is 900 newtons per millimetre. So if your panel is above, has the first three buckling loads, which are skin buckling, stiffener local buckling and inter-rivet buckling, if they're all above 600 it passes, and if the last two are above 900 it passes. So if it's a green light, it's good. If it's a red light, it's bad. If it's yellow, it means it's possibly a little bit over-designed. It's a little bit too high. And so let's just have a look at it in action, see if I can operate the mouse on the second screen. So let's just try changing my stiffener to another type. Let's just try a U stiffener and see what happens. Okay, so we can immediately see that when we change stiffener, the local buckling load of the stiffeners dropped dramatically because we've now got these big unsupported flanges of stiffener that are going to buckle. And it's also increased our weight. It's increased our T star. So because it's increased our T star, we get a little red light there saying that it's gone up. So let's put that back. And instead, why don't we look at, it turns out we had a pretty good design to start with, so we don't have to do too much fiddling. But let's try the skin thickness. If we reduce the skin thickness, the weight's coming down, but look, we've now got a structure that cripples and it skin buckles below the critical load. So that's not an acceptable design. Any red lights here mean that we've got something that would fail. So we have to get ourselves to a situation where everything passes. Well, not quite yet. Okay. Let's have a look at what the effect of changing the stiffener depth is. Okay, you can see quite a few parameters are affected by the stiffener depth. Stiffener pitch, this is a good one. Nearly everything in the model is affected by how far apart the stiffeners are from one another. Okay, so you can see we can start very quickly sort of simulating the effect of our design choices on the outputs. Okay, so all these calculations we've done today are embedded in the back end of this, and it's just displaying the results to you. So I'll build a little tutorial around this and we'll investigate how to design panels